everyone, I'm going to walk you through the fourth example from the circuit analysis lesson. So I've got my original circuit drawn up here, and the first thing that I need to do is calculate the equivalent resistance, and in order to do that I'd like to start by figuring out what all of the different pathways current can take through my circuit. So I know the current's going to start here at the positive terminal of the battery and here at the negative terminal of the battery, so I see two different pathways that current can take to get there. I think some current's going to go through this way, through that 1 ohm resistor, and then it's going to go down at this junction through the 4 ohm and the 2 ohm resistor, then through this other 1 ohm resistor, and then back over to the battery. So that's one pathway. The other pathway that other current can take is up here, also through this 1 ohm resistor. Oh, this is looking scary. Huh, let's try this one. There we go. Through this 1 ohm resistor, and then turning right at the junction, down through this 12 ohm resistor, and then back through that last 1 ohm resistor to the other side of the battery. So I see one place where current splits, which is right here after the 1 ohm resistor, and then those two current pathways come back together and meet up again over here before the second 1 ohm resistor. So the first thing that I want to do is condense these two parallel branches down, but I can only do that if I have only one resistor on each branch. Now the current that goes here through this 12 ohm resistor, it only goes through that one, so we're good here. But for this branch here, I see a 4 ohm and a 2 ohm resistor that are in series with each other. So the first thing I'm going to do is combine these two into a single resistor so I can get down to one resistor on each branch. So since these are connected in series, I can calculate the equivalent resistance by just adding them together. 4 ohms plus 2 ohms gives me 6 ohms. So then I'm going to redraw my circuit. I kind of cheated and did that already. Oh well. And so I'm going to say this is a 6 ohm resistor that replaces the 4 and the 2 right here. So now I'm back to a very similar circuit. I still have my current splitting here. I still have my current coming back together right there. But now, for each pathway between these 2 points, there's only one resistor on each branch. So I'm ready to go ahead and combine these in parallel. So to combine them in parallel, it's 1 over the equivalent resistance is equal to 1 over 6 ohms plus 1 over 12 ohms. Or in other words, the equivalent resistance is going to be equal to 1 over 6 plus 1 over 12 to the negative 1 power, which I do believe is going to give me 4 ohms. All right, so then I can replace this whole thing here with a single 4 ohm resistor, which I'm going to do right here. So that all condenses down into a 4 ohm resistor, and now I've got 3 resistors that are all in series. There's only one pathway around this circuit, so now I can just add all 3 of those together. So the equivalent resistance is going to be equal to 1 ohm plus 4 ohms plus 1 ohm, and that gives me 6 ohms. So then I can distill this whole thing down into a simple single resistor circuit that has a resistance of 6 ohms. So I found my equivalent resistance, and now what I want to do is analyze this circuit. So since this is the only resistor here, I know from the loop rule that the sum of all the voltage drops around the circuit has to be equal to the voltage of my battery. So all 12 volts has to be right here across this 6 ohm resistor. And so then I've got the voltage and the resistance. I can find the total current running through this circuit using Ohm's law. So V equals IR, or I equals V over R. So in this case, voltage is 12 volts, resistance is 6 ohms. That gives me 2 amps of total current running through my circuit. And so since that's the total current, I can actually do a really quick shortcut back up there and say that I already know that because this circuit is equivalent to this circuit down here, that they both must draw the same amount of current. So if this one draws 2 amps, this one also draws 2 amps from the battery. But I'm getting ahead of myself. So now that we've analyzed this version of the circuit, we're going to go back one step. So I'm going to take this 6 ohm resistor and split it back into 3 resistors that are in series. Now when I split resistors in series, the current stays the same. So this 2 amps right here, I'm going to copy for this one, and copy for this one, and copy for this one. The current has to stay the same. And so now that I know the current and the resistance for each of these components, I can use Ohm's law again to calculate the voltage for each of these different components. So voltage here is going to be the current, 2 amps, times the resistance, 1 ohm. That's just going to be 2 volts. Here the current is 2 amps, resistance is 4 ohms, so that gives me 8 volts. And over here I've got 2 amps of current, 1 ohm of resistance. That gives me 2 volts right there. And now I can look ahead and see that as I progress backwards through my work calculating the equivalent resistance, these 1 ohm resistors never change. I don't split them any further, they don't combine anymore, they just stay the same. So I can actually copy their voltage and current all the way back up again. So this one was 2 volts, and 2 amps, 2 volts, 2 amps, 2 volts, 2 amps, 2 volts, and 2 amps. Good. All right, so that's taken care of. But going back to this next step here, the difference is I'm going to take this 4 ohm resistor and split it into these 2 resistors that are in parallel. Now, when I have something that splits in parallel, the voltage has to stay the same in order for the loop rule to still be true. So since this 4 ohm resistor has 8 volts, I know that each of these resistors that it splits into must also have a voltage drop of 8 volts. And so now I can solve for the current along each pathway, once again, using Ohm's law. So current is equal to voltage divided by resistance, so it's going to be 8 volts divided by 6 ohms. So then over here, I'm going to have 1 1/3 amps of current. And then over here, this resistor has 8 volts and a resistance of 12 ohms, which is going to be 2/3 of an amp, 0.67 amps of current. Cool. All right. Now, this 12 ohm resistor doesn't change from this stage to this stage. So I can just go ahead and copy those values straight up. So we're good there, but the last thing that I have to do is take this 6 ohm resistor and split it back into these 2 resistors that are in series with each other. Now again, when I split a resistor in series, then the current has to stay the same. So since this 6 ohm resistor had a current of 1.33 amps, then I know both of these resistors must also have a current of 1.33 amps. And then from there, I can go ahead and multiply the current times the resistance to get the voltage for each of these. So I've got a current here of 1.33 amps times a resistance of 4 ohms, which should be 5.33 volts right here. And then here I've got a current of 1.33 amps, resistance of 2 ohms. And that gives me 2.66, 2.67, however we want to round, volts. Cool. All right, so now I've figured out for every component in my original circuit what its voltage is and what its current is. But if I'm not 100% confident, because I know there were a lot of places where I could have made a little mistake, what I'm going to do is use the loop rule and the junction rule to check my work. So the loop rule says that for any complete pathway from the positive to the negative terminal of the battery, all of my voltage drops along that way should add up to the voltage of the battery. So there are 2 different pathways here. For my red pathway here, I've got a voltage of 2 volts plus 5.33 volts plus 2.67 volts plus 2 volts. So 5.33 plus 2.67 should give me 8 volts right here, plus 2, that's 12 volts, which is the same as my battery, so that's good. The other pathway is this purple pathway, so that would experience a voltage drop of 2 volts here, plus another 8 volts there, that brings us to 10, and then finally 2 more volts right here, that brings us to 12 volts. So we're good with the loop rule. Our other way to check our work is using the junction rule, which says that any current going into a junction must be equal to the current coming out of the junction. So I've got a junction right here, and I can see that the current going into this junction is 2 amps, and I get that just by looking at the last resistor closest to that junction. So I've got 2 amps going in, And then the current splits two different ways. Now some goes to the right, and to figure out how much, I just go to the next resistor here. I can see that that's 0.67 amps going in that direction. And some current goes down. And again, I just look at the closest resistor. I don't need to add these two. I just look at the next resistor. What's its current? That's 1.33 amps. So 1.33 and 0.67 amps both leaving, going in different directions from the junction. That adds up to 2 amps. So 2 amps total coming out of the junction, 2 amps going into the junction. I am good to go. I have successfully analyzed this circuit.